I was just curious to see what you guys came up with. Peer review is a pretty good one.
Yeah, because that's a check and balance kind of a
Yep. Which is one we didn't talk about that, so that makes it a little more challenging. Better answer. Okay, so now that we got that settled and figured it out of the way, we can go ahead and move on. Of course, now it's going to be all more loud and shouty and we get this figured out. Now we actually have some official questions that we can actually start writing down. These ones actually require a little bit more writing down to a certain extent. That said, at least I think probably the first two, measurements, uncertainty, sig figs, rounding, almost all of those are just answers. You just write it down. So to kind of encourage you to actually write some more down, I want you to write out the question with the answer. Something to the extent of the question, like provide the number of sig figs for the following numbers. And then just list all the numbers and give me the number of sig figs. Maybe box those in. So all we're trying to do is get you to start thinking and actually start writing this stuff out. Okay? These are the numbers from PSS, so that's the 7th edition. If you have any other edition textbook, these numbers aren't going to necessarily match up. Okay? So that's why I've provided these headings behind it. Again, these are the headings coming from chapters or from edition 7. So the headings may have also changed in previous chapters. So what you're going to want to do is if you have a different edition, look for those key words. Okay? Look for measurements and uncertainty. If you see a question that says something about measurements and uncertainty, you should probably do a couple of those. Same thing for significant figures. If it asks you how many significant figures are in the following numbers, that's probably a good question for that. Okay? The idea being we can now use multiple textbooks. We didn't have to buy the same really expensive one. Okay? Questions about the homework. Okay, I got a question. When is it due? It is all of your homework is due the day of the exam. Okay, so it's not due next Tuesday. There is no real due date necessarily for it until the exam comes up. On the day of the exam, you will turn in your homework notebook to me. I'll flip through it, say, yep, you wrote some stuff down, give you points, and that'll be the end of it. So the homework, for the most part, is your practice, not for me. Okay? You will not get feedback on it unless you specifically come and ask me questions about it. Okay? Or you post your questions to the discussion board, and then I will try my best to answer questions there, though I'm finding I'm awful at checking the discussion boards. So hopefully you guys as a class can get together a little bit better, check the discussion boards more frequently, and try and help each other out and get those questions up there. All right? Questions about this? All cool with really? Okay.
Question.
Oh, okay. Yeah, go ahead.
I have a question about the extra credit. Is it 1 per week or after?
1 per week. Okay. 1 per week is the ideal circumstance. I'm not going to go back through and check heavily to make sure that you actually only did 1 per week. What I will check is if at the end of the semester I go back and look for your dialogues and I see 13 dialogues all within 1 week. That's kind of a red flag for not having things count. But if you happen to throw down 2 in 1 week, that's fine as long as you don't do it a whole, well, if you do it a whole lot, then you've way then cleared your 13 requirement. Okay? So the idea is that I'm getting you to think about it and start at least one way interacting with me to get you thinking about that material. Other questions? Within 24 hours of the lecture.
It's the same title every time.
Same title every single time. Other questions? Seeing some puzzling there. You got a question in that? No? Okay. Okay, we will go ahead and get started then. This is where chemistry is now going to bring in mathematics. So we've got to get an understanding of what these numbers are going to mean and how we've got to manipulate and use them. Okay, so to accurately pull information out of it. So what we're going to try and do is start quantifying our experiments. Instead of saying, oh, a gas formed or it changed colors, we want to be able to say this much gas formed or it changed this exact wavelength of color. We'll talk about that later too. We want to really be able to put some numbers down on it, and the intent being that if we're going to go out into peer review, we need to have somebody else get the exact same result as us. So that means we have to give them the information on what we got as a result so they can do a fair comparison. Okay? So we're going to be taking measurements. It's kind of the goal of chemistry, or goal of all science, get some measurement down. One of the biggest things that I've noticed that people tend to have problems with is you take a measurement and you say, okay, the distance or the length of my pen, okay, is 6. 6 what? Okay. All numbers are meaningless until we ascribe some meaning to them, which means when you report a number, you must also report the unit. Every number you write in this class must be followed by a unit. Okay? Which is going to get pretty tedious pretty fast, particularly if we went through and came up with an example. Okay? If I started doing some random math, said, okay, let's do some math, let's do, whoops, come back here. Say 2 plus 2 equals what? 4. Okay, you all agree with that, right? That's the math. What happens if it's 2 centimeters plus 2 miles? Okay, we can't do that. We have to make sure we know what those 2's mean. Okay, so every time you go through and write down a number, you must also specify the unit. I got a bit obnoxious here because I didn't tell you what those units were specifically. Okay, so what if, particularly in this chapter, you're just asked 2 plus 2? What should your answer be?
4 nickels.
It is 4 units. I know, that's going to be irritating. Deal with it. Okay? The idea here is getting you used to that point where you have to include that extra information with that number. Numbers are useless until we know what they mean. Okay? Make sense? Okay, so let's evaluate now some possible measurements that we could take. Take a look at distance or length. Anybody got a unit that we could use? Anybody? Meters. Anything else? Kilometers. Kilometers. What else? Centimeter. Man, you're picking the same units. I'm going to get rid of centimeters. Sorry. Yard. Thank you. Get something a little bit weird. Is grams a measure of distance? No. Feet. There we go. I like another one. What's another one? Miles. Inches. Okay, why go through this exercise? Well, if we're going to do an experiment and compare this to somebody else in the world, we have to make sure that our units match. So that when I say 2 meters, that 2 meters must be the exact same as somebody else on the other side of the planet. They have to measure 2 meters as well with that exact same stuff. So how can we ensure that that's what's going to happen? It's not even conversion yet at this point. Okay, we'll deal with conversion in a second. What we want to do is make sure that we pick one consistent unit system. One that actually makes sense. Okay. So if we go through and look at these, I have heard a few people hinting at what this might be. Which of these units is going to be the most appropriate for length? We're going to look at our meter system. Okay. Why would we skip the inches, miles, feet, and yard? What is an inch? Good way of phrasing it. America, yeah. Okay. Where did an inch originally come from? Not America, actually.
It's English.
It's English. Okay. It's the distance from some part on the king's thumb to another part on the king's thumb. I don't remember exactly where. For me, it's the tip of my thumb to my first knuckle, and that's 1 1/4 inches. Okay, why did I figure that out? Because I never carry a ruler with me. Now I can approximate inches. Okay. What happens when the king died and a new king showed up? You have a new inch, which means everything you wrote in the past is now wrong. You got to recalculate everything. Okay. What about feet? Where did a foot come from? It was the size of the king's foot. Okay. So they didn't have a nice, easy comparison system. Every time the king died, we had a new king, new feet, new inches. And the relationship between your thumb and your foot is not necessarily 1 to 12. okay, which is what we currently use. So what we want to do is pick a system that we can easily manipulate, and ideally we don't have to change the name too much on. So what do I mean by that? When we go from inches to feet, the name changes entirely. Okay? If we take a look at the meter system, if we were going to do similar comparisons, we could do centimeters or decimeters. Okay? Why is that better than inches to feet? What part of feet shows up in inches? Okay, I think the E shows up in both, but that's about it. There's no easy correlation to see that comparison. If we take a look at centimeters, decimeters, and meters, what do we start to notice?
Good.
Meters does show up. And what we're doing is we are changing the prefix in front. So in one case, we're looking at centimeters, decimeters. Okay? Those prefixes will carry very specific meanings. Those meanings are typically derived, or I think they're all derived from Greek or Latin roots. Okay? So if we have some understanding of our Greek number system or our Latin number system, we can start to imply differing measurements with a simple prefix change. Okay? It's not perfect, but it allows it to be easier and more consistent around the world. So when we look within science, most scientists will stick with this SI system as far as distances. We'll look at meters. And if we want to look at larger than a meter, we'll make it kilometers. Okay, so again, we change the prefix, but we're still looking at the same base measurement. Okay? How do we know what a meter is? Well, how long is a meter? I know we're all Americans. This is not going to help us. Anybody? Okay, you can't tell me I'm wrong. Meter, somewhere about this distance. Okay? How often are we going to use that measurement? Not very much. Why? America isn't always the answer, believe it or not. But it's pretty close. Okay, take a look at your textbook. Okay, let's measure your textbook. Does it make sense to measure it in meters? Why not? It's too small. Okay? Most of the things we're measuring are going to be on a much smaller scale. So we'll probably use other measurements or smaller units. Okay? In the case of your textbook, they tend to classify it as centimeters, being our primary measuring unit. Okay? And that's because if we scale down to a centimeter, roughly a thumbnail, that measurement is going to be a lot more consistent and easier for us to use because that applies to a lot more of the things that we would potentially measure. Okay? But now the next fun question is how do we know this is a meter? Along the lines of we don't, not exactly. Okay? How do we decide what a meter was? It's a tricky question. Somebody came along and said, wow, there's an origination there too. Could very well come down to that. I could see that as a stride. Okay. They came up with a standard measurement that they were happy with and said, okay, this standard measurement is now a meter. Ta-da, done. Except now it's not based off of a king or anything else like that. They said this is a meter. All other meters are going to measure up to this. So when you pick up a meter stick, how do you know that when they put that together that it was actually built as a meter? Well, what did they do? They went back to that first person that built the standard that said this is a meter. And they stuck up their piece of wood next to it and they said, yep, cut it right there. There, I got a meter. Duh, done. So all of our measurements are based off of some standard. Where is that standard then held? It's very much the same idea as the king. We measured it based off the king, except the king keeps changing. Okay? Our standards are stored in some special vault where they're under vacuum and they're highly protected. Why? Because if moisture gets in, that can cause materials to change their shape. What happens if we take that solid and we heat it up? Does it change its shape then?
It'll warp.
Yeah, it could potentially change its shape. It could warp. Worst case, it could melt and turn into a liquid. Okay, it's going to be really hard to figure out how long a meter is if it's running all over the floor. Okay? So we try and protect these things. And then when it comes down to what we want to establish what a meter is, we have to go back to that standard and do that strict comparison. Okay? So we do have these vaults where we've got meters measured out. We just have a fancy meter stick, okay, made out of very fancy materials. Materials that aren't going to be super subject to moisture and aren't going to be as subject to temperature changes. Okay, so if we go back and look at those, they aren't made out of wood. Okay, wood's got all sorts of problems associated with it. Okay? What happens if we now change to mass? What units do we have for mass? Stones. Old school. Nice. Stones. Grams. Pounds. This one's fun. We've got a ton, and then we also have an English ton. Careful. Gallon isn't a mass, it's a volume. So we'll come back to that one in a second. So again, we now have all sorts of different possible units. Okay, well, why do we have these units? Remember, these are all old methods for trying to measure different things. We didn't come up with the standard set until we could have enough communication around the world to be able to build these kind of ideas. So where did stones come from? Well, you got a bunch of heavy stones together and compared it to somebody else. Oh yeah, you weigh 5 stones. Okay. What happens if your stone changed size? Oh crap, now you weigh a different amount. That'd be a nice way to lose weight. Hey, I only wear 1 stone now. This is cool. Right? So we have to understand where they're coming from. When it comes back to the units that we're going to be concerned about in this class, okay, what's our primary unit, our standard unit? Grams. And if we want to scale up or down away from that, we can add in again a prefix. The other common one that people have heard of would be kilograms. Okay? Our gram unit still shows up, and what we end up doing is inputting again that prefix. That prefix is described by some mathematical term or conversion that allows us to simplify our naming, okay, or our unit names. What happens when we move to volume? Okay, we already heard one, gallons. Liter. Anybody else? Nothing else? You don't have anything else? Teaspoon. Nice. I'm going to abbreviate that one. I heard a cup in there. No nurses, doctors, aspiring drug addicts, I guess. Where I was going with that was a CC. Okay. Sorry, that segue didn't work very well. So CCs. Okay, again, which of these do we decide to use as our standard unit? Okay, we have to make sure that we're consistent when we apply how we're going to measure volume across the world. Okay, we see teaspoons and cups show up all the time. I'm talking to my dad, he hates it, but beside the point. Okay, what are those typically used in? Cooking. Okay, why have we not shifted away from teaspoon and cups when cooking? Okay, if you ever wonder why something hasn't changed, okay, this is just a horrible history lesson. You can trace that origin back to why something has not changed to an old white man.
What?
Yep, I blame men on this all the way through. Why? Okay, a lot of our origins behind these things come from power countries. You think back to when we first started to explore the globe. Who were the primary colonialists? English, France, Spain. Okay, we're looking at old countries with a predominantly white background. Why no women? It sucks, but I mean, okay. Why no women? Women really only got the right to vote within, what, the last 60 years? Is that right? Okay. Women weren't considered smart enough to do that, okay? Which is ridiculous when you go back and look at some of the amazing contributions that women have made. Okay? If you're ever interested in that, Madame Curie, if anybody's heard of her, absolutely amazing woman. Before they had the right to vote, before women had the right to vote, she had won the Nobel Prize twice. Okay? She discovered nuclear radiation. Well, not quite discovered, but she was a large supporter and founder and backer behind understanding that process. Okay? In a time where women couldn't even vote and decide what they could do with everything else. Okay? So it's really impressive the contributions that women can make, and it's really unfortunate they didn't get the choice. But that then makes it really nice for women, in my opinion, because then what can you do? Why is the system so broken? Because a man broke it. Okay? Thank you, or you're welcome, fellow men in the audience. So, what's happening with cooking? Okay, likely it came back to professional chefs saying, I don't want to change my standard measurement systems. Okay? So it's someone being very stubborn and typically very important about saying, I'm not going to change. Everybody must do what I say. Okay? When we get into science, what unit have we stuck with? Our bulk unit. Right in the middle there, liters. If we want to scale up or down, again, we add in our prefix. Take a look over at milliliters. Our prefix is that milli in front. Okay? Changing the scale of our liter volume in a very simple, measured fashion. Okay? Questions about that? What about time? What are some units on time? I heard hours, seconds, minutes, years, days. Okay, that's good enough. Stop. Don't get too many. Okay. Of those, okay, this is an interesting thing. How many different units do we really have for time? These all scale according to the same thing. Seconds relate to minutes. It's a certain number of minutes that we measure. Minutes are a certain, other way around, hours are a certain number of minutes. Days are a certain number of hours. Why on earth does it make sense for time to be the one unit that we have agreed upon throughout the entire world, but nothing else was agreed? Okay, we could compare it back to the sun on how often it takes to cycle around that. But if we go at different latitudes, we're going to see slightly different day length. If you go way north, you get really, really long summers and really, really horrendously dark winters. Okay, so it's not perfect with that alignment. Okay, my theory, and this is complete theory, and I'm definitely making stuff up, but I think it makes sense. Navigation. If you're going to sail around the world, you want to be able to come up with some consistent time measurement. How long did it take to get across? Okay? They used a lot of that for your navigation. You look to the stars to figure out where stars are, okay? And relate that back to time and around the planet. So to me, I think that's probably where we started with time being consistent, but I could easily be wrong on that. Feel free to look that up. It's always fun to be proven how wrong I am. Okay? But the point being that we have these standard measurements. We already know all of the ones within time. We grew up with all of those, doesn't matter where we came from in the world. All the other ones, if we're in the US, we're using non-standard units to us because we're used to all of those other ones. Okay? When it comes into this class, we really want to shift our focus and move into the SI notation. Meters for distances, grams for mass, liters for volume. Okay? That said, if you asked me to approximate a liter or a gram or a meter, you'll find I'm pretty awful at it. Why? Because I still grew up within the US as well. I'm used to those other systems. Okay, so it is going to take some practice getting used to working with these, but that's kind of the hope. The more you practice with these, the better off you'll get. Okay? Which of these units do we hope to hold and stick with as far as time goes? Why do you want to stick with seconds? Okay. Remember, our whole lecture point is trying to get you prepared for working in a lab, thinking about it experimentally. How do we design experiments? Now, think honestly to yourself. When you step into the lab, what's the first thought that crosses into your head? When do I get out? Okay. Which means, if you're going to monitor an experiment, what time scale do you want to monitor that experiment on? Seconds, because you can get done and out faster. Okay? Just so happens it works out that way. Most of our experiments will look at that second time scale. Why do we not go any smaller than that?
It's hard to measure.
Harder for us to measure. Think about your reflexes. Have you ever gone into, this is probably a stretch, but there's, I don't know if you've seen them where they show these little snake pictures and they say, okay, you're going to test your reflexes against the snake jumping out and biting you. Just push the button as soon as you see the snake move. And usually you find out the snake moves a lot faster than you can push the button. It's because your reflex is very, very slow. Okay? Our reflex response is on the order of seconds. We can go a little bit faster than that, but not by much. Okay? If we think back to what our eyes can monitor, we're still thinking on the second time scale. Okay? So it doesn't really make sense to look at how long something runs in the minutes or hours section, even though those can be easier and more accurate to measure, because they are longer, but we want to get out of the lab as fast as possible. And it's not just you. Every grad student on the planet does the same thing. Steps in, goes, okay, I want to go to lunch at this time. What do I have to do? Yep, okay, and now I'm out. Okay. So those are our standards for our measurements. So whenever you write down a number, make sure you specify your units. If you're measuring time, you should be looking for seconds. For volumes, you should be looking at liters, probably measuring in milliliters. Why not liters? Kind of comes down to safety. We approximate a liter. Okay, for me, the easiest thing is typically what size. You're going to buy bulk sodas. What size do you buy? 2 liters. Cut that in half. Fill it with acid. Now pretend you're walking around the lab with that. Okay, that's kind of dangerous, right? So if we're now going to work in a safe environment, we're going to try and limit your exposure to these toxic chemicals as much as possible. Likelihood that you're walking around with a liter worth of acid, not very high. We'll cut those volumes substantially lower to make sure that you're as safe as possible around them. Okay? Mass, grams is our standard unit for this. We might scale that back even further for the same reasons as we did with volume and move into milligrams. Just kind of depends on what we want to work with and how much we're working with. Lengths, we already talked about that one, looking at centimeters. Okay? Questions about that? How straight up boring is all this? 'Cause I'm seeing some yawning, heads down. It's just the lunch, right? The lunch rush? Yeah, that's the excuse. Whatever makes me happy, right? Okay? So our standards were invented. We have this stock collection of these, all of these measurements held somewhere. Okay? You think about time, we even have a standard measurement for time. It's been further refined as we advance with our technologies. If you go back and look at how long a second is measured by the decay rate of a particular atom. Okay? So we have very accurate measurements for each of these things. And in the more advanced countries, each of them have their own set of standards on which they refer to. Okay? So for the US, I think it's NIST, the National Institute of Standards and Technology. Okay? They keep a warehouse, not a warehouse, probably a small room with all of these standard measurements. Okay? So you could really mess with somebody by going in and changing them all. So distance and length. So we're going to try and figure out, say, the distance, or the length of this apparent metal rod. Okay? What are you guys going to tell me it is? Kind of hard for some of you to see. I'm guessing the volunteering is a little bit low. Let's zoom in. Boom. Zoomed in. What's that length? 4 1/4. Way to give me fractions. 4.25. Anybody else? Nobody else. Everybody thinks that is exactly 4.25. You serious? You guys aren't playing very nice. Come on. Okay, so there's a good addition. I can accept that. You don't want to do anything else? Like 4.1? 4.3 maybe? 4.2? Thank you. We're starting to get some numbers out there. 4.4? No, that one's wrong. 2.4. Okay. Okay, so we've got an idea on some possible measurements for this. You notice, since I forced you and twisted your arm into this, strongly encouraged you into this, notice when we look at those numbers, the 4 is consistent across every single measurement. Okay? What about the next number? Not so much. That varied a little bit. If we push all the way to even the last number, some of those measurements, we didn't even record a number out there. Why not? We were just making it up. Have no idea what's out there. Okay? What happens if we now change our ruler? Now what is it? Don't tell me 4.25 again.
4.296.
Okay. There's some volunteering. 4.296. Anybody else? 4.25. Anything else?
4.3.
No, not quite.
Yeah, it's a little bit shy of 4.3. 2.7. Why go through this comparison? Well, what happened? We take a look at our numbers. Our 4 is now consistent across all of our measurements, and now so is our 2. Okay? We've added some more information about our measurement by adding in these extra hash marks. Okay? So what we're looking at now is kind of the accuracy of our instrument. If we have a ruler that only measures out, how'd you guys know it was centimeters? This morning swore it was centimeters too, and I didn't see it. Oh, it said centimeters before? Okay. I believe you. Okay. If we look at the first hash marks, that only marked out every centimeter. If we look at the next set, it starts to mark out some more delineations. We can now measure a little bit more accurately. We can specify a number more accurately. So this is going to start to bring in some more accuracy towards our measurement, which is a nice thing. Okay? But a lot of it depends on how accurate we want to get as well. So each instrument is going to incorporate its own error in the measurement. And so technically, we should report that error whenever we report the number. So in each of these cases, yes, we're specifying a number. And I did the unit on almost all of them. But we should also add an error that the instrument brought into it. Okay, so that way when somebody goes through to compare, they know to either believe our measurement or not. Why did no one come up with, just for the heck of it, 4.2643, why not 1, 9, 7, 2, that's a 6, 2. Why did we not come up with this measurement? Because at this point, all of those numbers we're dropping out there completely made up. Okay, we're guessing entirely at that. We have no idea. We have no way to specify that those numbers are accurate. Which means when we're going to report our number, we can't include all of those numbers, or we shouldn't include those numbers, because what we're trying to provide is what we have evidence to support, not just guesses at what might be out there. Okay? So when we go through and report our individual numbers, we should report the uncertainty. So in the case of the first ruler, we might report that as 4.1 plus or minus 0.1 centimeters. Okay, why 0.1? Because when we go through and look at all of the possible measurements, we've had a whole bunch of different people measure it out and come up with it. I should have made you write it down, so that way you all had to shout it out instead of letting one person do it and just pay attention to them. Okay? We would go back and look and say, okay, what was the number or the numbers that stayed the most consistent or had any variability within them? In this case, we had that last digit, And that's where we had a lot of variation. So we would incorporate that into our answer. We'd say we've got plus or minus this error associated with it. What happened with the second measurement? Second measurement, we were consistent with the 4.2. Where we had problems was with that third number. So we could go through and say a plus or minus, and again, we would now incorporate our error into the measurement. If we go based on what the slide said, say plus or minus 0.05. Any idea why we did 0.05 as opposed to 0.1?
You're identifying if that's not the one that you're certain of.
We're not specifying the specific number. So I see that pattern that you're talking about there. That's not actually where it's coming from.
So you're not saying we're uncertain about the 5?
Nope. All we're saying, we're putting a number here where our error is associated with.
Yeah.
That number can be anything. It does not have to match that.
So it could be 1 or
It could be 1 or more. How would we know that? We'd have to go back to all of our experimental values for the same thing and say how much did they vary by. So this variation at the end is something that you guys would find on an instrument. If you used a balance, okay, it would tell you it is accurate to 1/10 of a gram. So when you report it out, you would say plus or minus 0.1 grams. Okay? How would you, looking at a single number that you've got, determine the error? Good for you. You don't. Yay! You don't have to worry about it. Okay? What you need to be aware of, though, is that these numbers come with errors. This error does impact your overall result. Okay? We do not expect you to be able to predict what these errors might be. You should be able to pick out maybe the decimal value, but not much more than that. Okay? Kind of makes sense? Okay. So when we go through to measure mass, one of the fun things about mass is that it's often confused with weight. Weight is based on gravity. Mass is based on mass. Okay? It's what made up that compound. Okay? When we look at our weight on different or in different gravity environments is going to change, but our mass will not. So when you step on the weighing scale, it's not a weighing scale, what do we call it?
Balance? Scale?
Scale? Is it just scale? You walk in the bathroom, put it down. What do you put down before you step on it? Scale? Okay. I'll accept it. Thought it had a different name. That's why I'm not an English major. I'm a chemist. Okay? So what we're looking at is looking at that scale. What is it giving us a number of? Really what it's doing is approximating our mass. Okay? So someone has calibrated it to approximate the mass of the object that's on top of it. Okay? It's not perfect, but it's an approximation. It allows us to give us some idea of if we feel really heavy or we don't. Okay? Kind of an arbitrary system. Nothing particularly fancy about it. Okay? But if we go through and measure the mass of something, okay, that mass is not going to be dependent on gravity, hence it's not a weight. If we go through and look at these balances that are adjusted here, if we take that balance and take a 10-gram weight, okay, well, that's a bad phrase, a 10-gram object, and put it on our balance, okay, we could then adjust this mass that direction until it balanced out. It evened out. We say, okay, now it weighs 10 grams. Okay? What happens if we now take that to the moon or into space?
Take it out of gravity so it changes.
It does not change.
Oh, the mass.
The mass does not change. So what we would record on this balance is the exact same. But why? Okay, the weight of that thing very clearly changed. But when we go through and take a look at the mass is being compared. Our object mass is being compared to the mass over here. So when we move up into space, what happens? The weight of our object changes, but so does the weight of our standard on which we're comparing it to. Okay? So when we look at mass, we have to know that standard on which we're comparing everything, and that must be super accurate so that when we do the comparison, we know what the mass is, not the weight. Okay? Kind of an interesting, tricky topic. Not too big of a deal, just realize that what we're dealing with is always a mass. Okay? We're going to look at volume measurements. There's a variety of ways that we can measure out volumes. And a lot of that is just going to depend on the accuracy that we want. Okay? You got graduated cylinders, syringes, burettes, pipettes, volumetric flasks. All of those are going to measure slightly different accuracies, and that accuracy is what we're really going to be looking for. Okay? If I want to know roughly what 2 milliliters is, I might use a graduated cylinder. If I need to get it down to 0.0000, I might want to use a volumetric flask or a pipette, okay, or volumetric pipette. So the instrument brings with it some error. Depending on what we want, we'll do different things. Okay, I mentioned the unit for volume, and I forgot to come back to it. We had cc, typically seen with our syringes. What is cc? It's the same as milliliter. It's a cubic centimeter. The exact same thing as a milliliter. So why do we call it cc's and not milliliters? Your guess is a good mine, I really don't know. This morning I said cc sounds a little bit cooler than ml. Give me 50 ml stat. cc sounds a little bit cooler. So does stat. Okay. Significant digits. So this is where it's going to be kind of fun, and we're almost, or by fun I mean confusing, is trying to understand what numbers we should be reporting. Okay? If an instrument gives us a sequence of numbers, say we put a mass on our balance and it tells us that the mass is 10.0000, what do you write down? 10.00, I already forgot how many zeros. Let's say 4 zeros. 0, 0, 0, 0. Okay? We have to report all of those zeros because the instrument gave us that information. Okay? The instrument is telling us that every single one of those is significant to the mass of that object. So we have to report it. Okay? So in the real world or in the lab, your instrument's going to give you that information. It's relatively easy to figure out what your significant digits are because you're told it. What happens when we move to the lecture? How many of you have a balance in front of you? How many people don't have a balance in front of you? I'm getting a little bit more participation that way. Okay, so we don't have balances here to actually look at these. Okay? We don't have syringes. We don't, ooh, that was a bad example. Graduated cylinders. Okay? We don't have these measurement devices in front of us to identify what our significant digits are. Okay? So what we're going to have to do is try and determine, based on some random number now thrown at us from the textbook, how many of those numbers are significant. So that when we go through and try and use calculations, we make sure, or try and do calculations, that we make sure those significant digits are transferred across. So what makes a number significant? Any ideas? Okay. Our first rule is all digits 1 through 9 are always significant, every single time. Okay. What happens with 0? Is 0 a number? Technically, yeah, it is a number. Probably one of the more difficult mathematical concepts. Okay, until we discovered the idea of 0, okay, math kind of stalled out. As soon as we bring in the concept of 0, now we've got all sorts of fun things that we can incorporate. Okay? So we need to then figure out, is 0 significant? Well, it turns out not always. Okay? We need a little bit more information than just that we have 0. That extra information is going to be the decimal point. Okay? A critical piece of information when dealing with significant figures. Okay? It is kind of the be-all, end-all. You need that decimal point. With that decimal point, we can now really nail down our significant digits. Okay, so what do I mean by that? So what we're going to do is look at some examples here. All digits 1 to 9 are always significant. So I didn't put this number up here, but let's go ahead and try it. Let's say we started with 12. How many significant digits does that number have? 2. Okay, we have a 1. According to rule number 1, that is a significant digit. 2 is also between 1 and 9. We have a significant digit. We've got 2 significant digits in 12. Okay? What happens if we now move to 102? Okay, according to rule number 1, we've only said numbers 1 through 9 are significant. So at very least, we've got 2. The 1 and the 2 are significant. Okay, so I'm going to go through and underline our significant digits. But what about the 0? Okay, that's where we need to specify some extra rules. So we can move to rule number 2. If there is no decimal point, then the 0 must be controlled. Okay, or I'm calling it controlled by significant. Sorry, I gotta grab that. By significant digits to both sides. Okay, so if we take a look at 102, was 100 significant? Or sorry, 1 significant?
Yes.
Was 2? Yes, what does that mean the 0 is? Significant. We count it up, we get 3 significant digits in this number. Okay, questions about that so far? Let's push to the next one. 120. According to rule number 1, numbers 1 to 9 are significant. So 1 and 2 are significant. Okay, now we've got to evaluate our decimal point. Rule number 2 says if no decimal point, which we don't have, then the 0 must be controlled by significant digits, meaning we have to have a significant digit to either side of it, okay, both left and right. So we take a look at our 0. Do we have a significant digit to, what is that? It's left. Yeah. Yes. How about to the right? No. Which means the 0 is not significant. So our number of significant digits becomes 2. One more example on this. Let's add another 0. How many significant digits? Still 2. We go through and evaluate the same way as we did everything else. The 1 and the 2 are valid. We move to our next 0. We look at that 0 and we say, okay, I have a significant digit to the left. Do I have a significant digit to the right? No. If that digit is not significant, the 0 in the, or what is that, our first 0 is not significant, that also then implies the last 0 is not significant. We still end up with 2. Okay? Questions about that?
Yeah, I don't get how, I mean,
Yep.
you go from 120, so if you drop the 0 off 120, it goes down to 12.
So
you just
be
change the value.
careful. We are not getting rid of the zeros. We are reporting the significant digits. Okay? Where those numbers appear as far as their place, so the ones, tens, hundreds, thousands place, we do not change. Okay? So that number is still 1,200. Within 1,200, there are only 2 significant digits. So the zeros still carry meaning, but they aren't significant meaning. Sounds kind of goofy.
Isn't their value is the most significant part of the numbers? Does that make sense? Like, that just seems,
I'm not going to lie, it definitely seems odd, but that's what's happening with this. Those zeros are acting as placeholders to make sure that the 2 is counted in the hundredths column or in the hundredths place. Those zeros are holding in their positions to make sure that the 1 is counted in the thousandths place. If we remove the zeros altogether from that, now where's the 2? 1's place. Okay? So the zeros hold meaning for the place on where our numbers belong. They don't hold significance as far as calculations, which is kind of a weird thing to say. Calculations would go later on. Okay? So when we go to add and subtract different numbers, we still hold, those zeros will force our other numbers into particular places, but they don't count as far as the numbers that we would need to retain for our calculations. Okay, so this is odd because we're breaking it up and looking at first identifying an individual number for significant digits, and then we'll shift into the calculations. So hopefully both will help congeal this a little bit. Unfortunately, we're really only going to get through this section of it. We won't get to the math today. What happens with the next number? 120 decimal point. Okay. We now have our new rule. If there's a decimal point, then the 0 only needs to be preceded by a digit to be significant. That means the number directly in front of it needs to be a significant digit. In the case of 120 decimal point, is it? The number in front of it, is that a significant digit? Yes, which means 3 sig figs. What happens with 120 decimal point 0? The 1 and the 2 are significant digits, so let's take a look at our 0. Is it preceded by a significant digit? Yes. And you got to be careful with what zeros I'm looking at. So now let's move to the next 0. Is it preceded by a significant digit? Did we just underlie it and say that that was a significant digit? Absolutely. How many significant digits show up here? 4. So it's going to come from how you evaluate this, the order in which you evaluate. Evaluate left to right when trying to determine the importance of zeros as being significant or not. Okay? Okay. What happens when we move to the top right? Decimal point 12. 2 sig figs. We only see 2 numbers there. 2 sig figs. What happens when we get 0 decimal point 12? Still 2. Why do we not count that 0? Okay, we go back to our rule. It must be preceded. That means it must be to the left. There must be a significant digit there. Do we have a number 1 through 9? No. Which means 0 does not count as a significant digit. We're left with 2 numbers. Why do we include the 0? Kind of has to do with the placeholder. Really what it does is accent the fact that we have a decimal point. In the lab, okay, since I don't think very many of you have me, if you did have me and you wrote a number like this up here, what you would see is a giant circle and me say leading zeros. Or leading 0. Why? If you're writing something out, draw a decimal point for me right now. Probably just a, right? Pencil straight down. Okay? Is that a real mark or was that a stray mark? Okay? Hard to tell the difference. Okay? If you put the 0 in front, the only reason the 0 is in front is because decimal point's coming right after it. Okay? So that leading 0 helps us define and ensure that when we make a mark for a decimal point, that we know it's a decimal point. Okay? So it helps kind of minimize that stray mark error. What happens with the next number? Still 2. Our 1 and our 2 count as significant. The zeros do not, because if we look what precedes, okay, so if we start left to right, our first 0 is preceded by nothing, which means not significant. We move to the next 0. What is it preceded by? Not a significant digit, not 1 through 9. Doesn't count. We still end up with 2 significant digits. Last one, we get 3 significant digits. Our zeros in front do not count. The 0 at the end does count now because it is preceded by a number or a digit between 1 and 9, a significant digit. Okay? Kind of makes sense? Okay. I know it's going to take a little bit of getting used to process and follow. If you do follow these rules, I'm actually surprised at how well they work because I made them up. I didn't like the way the textbook described it at all. It confused the heck out of me. So read through the textbook. If you don't like the way I've described it, check the textbook. Maybe the textbook will describe it to you in a way that you understand better. You will get the exact same answer. These slides are online. Yep.